Welcome back to One Sample Z hypothesis testing. So, Beauty Haven, a popular makeup store near campus, believes that the average price of their best-selling makeup products is lower than the national average for similar items. The national average price for these makeup products is $25, with a known standard deviation of $4. The store randomly samples 30 of their top-selling makeup items and records their prices. At 0.05 or 5% level of significance, they want to test if their average price is less than the national average. So here's the sample that they took from their own store. And we'll calculate the average for that sample. And here's the national average. So clearly there's a difference there. Our task is to see if that's a significant difference or not, or could be just sampling error. So the sample size is a count of these items. And since they gave us the standard deviation for the population, we're going to go with that, which is sigma. And that's 4. It's given in the problem. And alpha is 5%, also given in the problem. So our expected variability here, or standard error, or sampling error, is the standard deviation of x bar, or the standard deviation of the sample. And that is the regular standard deviation divided by the square root of n, or divided by the square root of the sample size. We're looking at x bars. See, there's a bunch of x bars. And it's going to be a z-score. And it's the probability of x bar. So the distribution here is normal for the hypothesized distribution, which is called mu0, which is all these x bars. And remember, so you don't get confused about this, this is kind of like the cookie jar again, where you've got a bunch of samples of cookies. Some samples are more likely than others. We're trying to figure out, is this one of the more likely samples? Comparison, in this case, we're looking for the critical value. And now the question is, notice that we've only got one line now. So we're only looking one direction. The direction is lower. Lower means to the left. And it's not going to be quite that big. We'll find out just how big it is in a second. So the hypothesized mean from the problem is 25. Expected variability is going to be equal to, remember, sigma divided by the square root of n. There's sigma divided by the square root of n, 0.73. X bar in this case is, well, we can't actually just say equals, because we don't know x bar for the critical value. We know it for the test stat. So we actually have to work the other direction, starting with the probability. That's going to set where that x bar is for the critical value. So the probability is equal to 5%. And the reason I don't divide by 2 this time is because I'm only looking one direction. So all the probability goes on one side. And then, again, it's p of x bar to x bar. We're looking left, so it's norm.s dot inverse equals norm.s dot inverse of this probability. And then x bar is going to be equal to that z-score times the standard error. And that difference from the mean is going to be added to the mean. So we see how far away we are from the mean, which is the 23.80 down here. Okay, now let's worry about so that's the cutoff. And you notice this is a slightly fatter tail than we're used to seeing because all the probability is in that one side. All right, the test stat, again, the same hypothesized distribution. it's also going to be to the left, right? We know that because it's less than the 25. And the hypothesized mean is still the same. Because really we're trying to see, does it belong to the same distribution, which is why expected variability is also the same. All right, now we do have this sample mean because we calculated it right there. So that's why the arrows are going this way, we're moving this way. And then the test stat, when you're going that way, x bar to p of x bar, is going to be x bar minus mu divided by the standard error. So that's equal to that x bar or that sample mean. Oops, got to be in parentheses. Minus the, minus mu minus the sample mean minus the population mean divided by the standard error. And then the probability of that, when you're looking left, is just norm.s.dist. All right, so this is going to be statistically significant. We're definitely in the rejection region. And so that's kind of exciting. It means that our price is definitely below the national average. It's more than just sampling here. All right, so H0 here is that they would be the same. But now our alternative hypothesis is going to be different than what we usually do. On a two-tailed test, we always go, well, they're just not equal. But this is a one-tailed test. So we're only testing one direction. And we're saying, if they're not equal, then we're less. That's the alternative, which is going to turn out to be true in this case. The standard error is the sampling error, which for all these is measured by sigma x bar, which is the standard deviation divided by the square root of the sample size. All right, the test statistic is a z-score, the critical value. Our test statistic is less than the lower critical value. Here's the lower critical value, we're less than that. And our probability is less than alpha, right? Here's alpha 5%, our probability is just 0.4%, so we're less than that. And so, as a result, we are going to reject the null hypothesis, because that 2308 is unlikely to have come from a population whose mean is 25. So we accept the alternative, and the alternative is that we're less than. All right. Now, approximately what raw value is a whole number is the lower cutoff. Lower cutoff is right around here, so the whole number would be 24. What is the raw difference between the critical value and the new sample x? So it's 23, the difference between 23.08 and 23.80. So that's 0.72 difference. Now this says, what are you estimating with the confidence interval? Well, we haven't calculated that yet. This is new in this problem. So let's go up here and do it. So what's a confidence interval? We didn't do it for the first two, but it's actually a good thing to do for all of them. And that is, what you're saying is, look, I'm fairly sure that the population mean for this sample is not this population mean. But then the question is, well, what is it then? And so you can actually calculate it, not precisely, but you can give a range of where the population mean for this sample must lie. And you do it by first calculating what's called the margin of error. And as you can see here, we have two formulas for that. The first formula is for a z-test, which is what we're doing. The second one is for a t-test, which is what we'll be doing in another module. So we're going to use norm.s.inverse, 1 minus alpha divided by 2 times the standard error. So we say equals norm.s.inverse inverse 1 minus alpha divided by 2 times the standard error, which is sitting right here. So that's our margin of error. And now that is the distance that you go either side of your sample mean. So we take the sample mean, which is this one. We could also have taken it from here, minus the margin of error for the lower bound. And then we take the sample mean plus the margin of error for the upper bound. And when we do that, we get a green line here. And that green line is basically telling us where the true, it's the word that they use, the true population mean that the Beauty Haven sample came out of is somewhere between 21.65 and 24.51. We don't know exactly where. We imagine it's probably somewhere in the middle, and that this is kind of its own distribution above it. But the one thing that you really should notice is that if this is statistically significant, which it is in this case, then that confidence interval will never cross the hypothesized population mean, right? It can't, because if it did, then this would have been a reasonable, this would have been within that 95% margin of error for this, confidence interval for this. So it can't. So it's somewhere in here. So now we can say, what are you estimating with the confidence interval? We're estimating the true population mean for Beauty Haven from which our sample came, which we now think is not the same as the national hypothesized distribution. What's the size of one standard error? We get that from the graph, 0.73. And what is the raw value at negative 2.262 standard errors? Which is right here, it's 23.08. All right, now we're also doing something else new in this problem. So not only are we calculating a confidence interval, but we're also calculating Cohen's d, which is called effect size. And what this means is that when you find something statistically significant, which we have, right, we know it's statistically significant, but now we're saying, okay, fine, statistically significant, but is it a big deal, right? In other words, should we make a business decision based upon that? And Cohen's d tells us whether or not we take the additional step of actually making a business decision. So we're looking at business impact. And the way it's calculated is to take x bar minus mu divided by the standard deviation. So equals x bar minus mu divided by the standard deviation. Somehow I made a mistake. Let's see. Oh, because that's not x bar. That's x bar. Maybe I probably should have picked this mu too. Not that it matters. There it is. Negative 0.48. All right, now, the negative sign in Cohen's d doesn't matter. All we care about in Cohen's d is the absolute size of this difference, no matter which direction it is. So for all intents and purposes, that just means 0.48. So you find 0.48 here, which is somewhere between this one and this one. So we're going to go with this third one. It's a noticeable impact. So that means actually is a big deal in competitive environments, improved sales performance, which is what we would want, small stock price changes. So this is worth acting on. So let's go for our recommendation. It is statistically significant. The business impact is a noticeable difference. So action, absolutely. Take action, right? Get behind this this price change, because that might actually lure in more customers. And we'll see you in the next video.